Richard James Mathematics Resources will present Grade 4 Practice Paper 5. We are beginning, as usual, with Video A. In each section we have 4 videos, A, B, and C. Videos A to C each contains the solution of 12 problems. We will begin at the beginning at problem number 1. What is the value of 229 plus 47? And Jerry is right there telling me, what do we do first, Jerry?
Add.
Well, that is the use of the symbol that we have right here. But what do we do first?
Put down the numbers.
Alright, so we'll write the numbers down. And we'll just put 229 first. So let us add the numbers by writing down the first number first. Write down the place value of the digits, beginning with the smallest place value, which is? What is it? Right. And we will start with the ones. The tens and the? Okay, the hundreds. Next, write 47. Which one of the digits do we put down first, Jerry?
The 7.
Right, and that 7 will be placed where?
Under the ones.
Okay, because we have 7 ones. What about the 4?
Under the tens.
I was trying to trick Jerry just now by getting him to say write it under the hundreds. But he insisted that we put it under the?
Tens.
Right. So place the tens digit under the tens digit. Like that. Write your addition sign and draw your line. Begin by adding the ones digits. The ones digits, when we add them, Jerry, what will be the result?
16.
Alright, look at this now, Jerry. 9 plus 7, that's 16. Take a look at what will happen if we put the entire 16 down. The 6 in the number will be placed in the ones column, and the 1, which is the tens digit, will be placed in the tens column. Would that be acceptable, Jerry?
Yes.
Right, it would be acceptable, but if we do that, the addition process will be confused because we still need to add these and the result needs to be in the tens place value position. So what do? Take a look at what will happen if we put the entire 16 down. The 6 in the number, the 6 in the number will be placed in the ones column, and the 1, which is the tens digit, will be in the tens column, like we have it right there. If the 1 remains, it will get in the way of the sum of the tens digits. That is why it is carried to the top of the tens column. Alright, it is carried where? To the top of the tens column, so that it does not get into the way of the remainder of the process. Add the tens digits. What do we get?
7.
I hope that's the same thing that we'll get. 1 plus 2 plus 4, and that is equal to 7. And finally, for the hundreds digit, there is nothing to be added to the 2. It will return as it is. Place 2 in the hundreds column. That answer is represented by?
Option B.
It is represented by option B. The correct answer is option B. Here we have our box as we had in volume 4, or a square. 2 box 12 is equal to 24. What operation does the symbol box represent to make the statement true? We can call it anything. We can call it square, or we can say blank. 2 blank 12 is equal to 24. What operation does the symbol blank represent to make the statement true? What should go right here, Jerry?
2 times 12.
Right, so that's 2 times 12 is equal to 24. Therefore, the operation that should go there is multiplication. But we'll just take a look at the others. 2 minus 12 is equal to negative 10. And 2 divided by 12 is equal to 1/6. These arithmetic operations do not fall into your regular arithmetic at this level, and neither of them is equal to 24. So if we take a look at the subtraction or the division, we will get results, or we will go through a process that is not in touch with your mathematics at this level. Furthermore, the operation will not give 24, so those are not correct. 2 plus 12 is equal to
14.
Neither is addition the correct operation. However, at this stage, we all should be sharp on our 2 times table. We should not need to go through any process of elimination nor any unnecessary calculation. So, we do not need all of that. 2 times 12 is equal to?
24.
That's just for your 2 times table. The correct operation is multiplication. And the correct option is therefore option
A.
Nice. At this stage, students should be able to see in an instant that multiplication is the correct operation, especially that it is the first option. Right? There's no student who should have any difficulty with your 2 times table. With your 2 times table, therefore you should not go through any long and lengthy calculation to see that multiplication is the correct one. And it should be even more obvious that it is in the first option. $2,472, and we need to divide that by 6. How do we do that? Long division or short division, Jerry?
Short.
Jerry is saying that it is short division because he does not want to waste any time. Probably wants to go and play football. Jerry does not want to set aside time for mathematics. He wants to be in and out in a flash. He will use short division. Well, look what will happen to you on this occasion, Jerry. When dividing by any number, we are dividing by 6 in this particular case, focusing on the multiplication table will help. We are dividing by what in this case, Jerry?
6.
So what multiplication table should we pay attention to?
6 times.
Right. So let us put that down. There we have our 6 times tables, just a few of them, and they are all gone. Why are they all gone? Because I do not want you to be dependent on something on the screen when you should be all sharp on your multiplication tables. So we have 2,472, and that we need to divide by
6. And the answer is 412.
And the answer is 412. Jerry is saying that it is 412, and that is why he is asking me to do it short division style, because he's able to just look at the screen and tell the answer, even without writing down anything. That is how sharp Jerry is on his multiplication table, his arithmetic overall. So let's see what we do here. 6 into 24 goes
4 times.
6 fours.
24.
Okay, no problem. We will first attempt to divide 6 into 2. We can't, so we say 6 into 24 equals 4. And place the 4 above the 4. Right, so it is 24. So the result should go over this one. Let's take this back out. So we will say now 6 into 7.
1.
6 ones.
6.
Right. So we know that 6 does not divide into 7 evenly, or we say that 7 is not divisible by 6. 6 does not divide into 7 without leaving a remainder. But 6 can go into 7 how many times?
1.
We will then say 6 into 7 goes 1 time. The 1 will go above the 7. But 6 times 1 is equal to 6. There will be a remainder of
1.
that will be reduced in size and go besides the
12.
Okay, so we have short division. We say 6 into 7 1 time. Then we say 6 1 6. So there's a remainder of 1 and it will go beside the 2. We intended to write it as 12. I will not let out my secret as yet. Let me solve the problem first. Finally, we will say 6 into
12.
goes how many times?
2 times.
2 sixes.
12.
Okay. This time, we will say what? 6 can go into 12 exactly 2 times. And the answer is 2. And that will go right above the 2 that we have right there. So, the correct answer is therefore option
D.
as Jerry stated earlier on. The correct answer is option D. On the next slide, this is what Jerry does not want, because he just thinks that I will just work it out one way. He does not want me to work it out long division because he just wants to run away. On the next slide, we will use long division in solving the problem. Continue to bear your 6 times table in mind. Long division. We'll set it up like normal. Attempt to divide 6 into 2. We can't. So we may say 6 into 24 equals
4 times.
as before. And place the 4 above the 4. So we say then what? 6 fours.
24.
That's what we will do. We say next 6 fours 24 because we are doing long division and we intend, just in case we do not have an even division, we will make use of the remainder. So we need to say 6 fours
24.
and subtract the result from 24 because we are saying 6 into 24 is 4 times. 4 sixes 24. So we will subtract it there. When we subtract, what do we get?
0.
0. And what will happen? Let me ask what Jerry. Ask Jerry.
Carry down the 7.
Alright. So Jerry said that we should carry down the 7. So what we will do, take the instruction from the slide. The 7 will accompany the 0 as the next number to be divided by 6. So the 7 will accompany the 0 as the next number to be divided by 6. So Jerry, is that correct to have the 0 right there?
Yes.
Or it is correct to have the 0 there?
Or you could put a dot.
Okay. Or we could? Or what can we do?
Put an X.
or we can erase or remove the 0. So a leading 0 does not affect the value of the number and may be discarded. So we may throw that 0 away because it does not affect the value of the number that we have there. So as Jerry said, that we should bring the 7 down. So the 7 accompanies this 0 there as the next number to be divided by 6. Then what do we say? We will then say 6 into 7 goes
1 time.
1 time. And then what do we say after that?
616.
Right, 616. So 616. And we will subtract that 6 from the 7. 7 minus 6. What will that give?
1.
7 minus 6 equals 1. And what do we do next?
Carry down the 2.
Right, so we will then cause the 2 to accompany the 1. Right there. And what do we say then?
6 into 12.
6 into 12 goes how many times?
2 times.
Exactly 2 times. And then we will finish up by saying what? 6 twos.
12.
Say 6 twos 12 and subtract the result from the 12 that we have right there. And when we are dividing, bear our multiplication tables in mind, so that we may say, what number do we multiply by 6 and the result is 72, or what number do we multiply by 6 and the result is 24? The numbers are exhausted. Therefore, we have used up all of the numbers that we have up here. We have used them up. So when we subtract the 12 from the 12, the result will be 0. There will be a remainder of 0. Also, there is no other digit in the dividend. We have used up all of the numbers that we have here. The division process will therefore come to its end, because we have used up all of the numbers that we have there. The quotient, which is the answer, will therefore be 412. And that was represented on the previous slide by which option, if you can remember, Jerry?
Option D.
Right, you're on your game. Which number is missing from the sequence 18, 21, 24, dash 30?
27.
Jerry said that the one that is missing is 27, and he's laughing. If it is not 27, Jerry, you will have to pay. So let's see. When manipulating or interpreting a sequence, there are 2 things that we need to bear in mind. Use the first one in this first approach in solving the problem. There are 2 things that we need to bear in mind when we are solving a problem involving a sequence. 1, terms in a sequence are related to each other. 2, let me say that again. Consecutive terms in a sequence are related to each other. And the consecutive terms are related in the same way. 2, terms in a sequence are related to the set of counting or natural numbers. So there we have our sequence with the blank one left out. Consecutive terms of a sequence may be shown to be related. If you can find how they are related, then we can generate the entire sequence. Now here's your question. 18 to 21. 21 to 24. What is consistent there? What do you notice is consistent there, Jerry? If we go from 18 to 21, that's what?
3.
And if we are going from 21 to 24, what's that?
3.
Right. So in going from 18 to 21, we added 3. And going from 21 to 24, what did we add?
3.
3. So in going from 24 to this one, what should we add?
3.
Right. And if it is correct, when we take this one and add 3, then we should get 30.
Yes.
So what is true that links 18 to 21? 18 plus 3 is equal to?
21.
And also 21 to 24. 21 plus 3 is equal to?
24.
Right. So we keep adding 3 each time. So the sequence seems to be increasing by 3 each time. I am not saying that it is increasing by 3 each time, because if the rule is broken somewhere in the middle, then we will have some difficulties. We are just using what seems to be the case, and by putting it through the test, then we may prove that it is actually the case. So 18 plus 3, that's 21. 21 plus 3, that's 24. The sequence seems to be increasing by 3 each time. That being the case, for the missing term, increase 24 by 3. So that will do for the missing term. 24 plus 3, and that is equal to?
27.
27. If that is correct, then the same rule should give 30. Does it give 30?
Yes.
Add 3 to 27 and the result is?
30.
Right, so 27 plus 3 is equal to 30. It does. The correct answer is therefore option
C.
Right, so we tested the sequence to see what is happening there. It seems as if it is increasing by 3 each time. So we increase 24 by 3 and we get 27. If that were correct, then adding 3 to 27 should give us the other term of the sequence that is there. And it does. That means we are sure that the correct answer is?
27.
Correct. The same problem. What we just did is that we used the fact that in a sequence, consecutive terms are related to each other. Now, we will use another property of sequence, which is that terms in a sequence are related to the set of counting numbers or the set of natural numbers. The other approach is beyond the scope of grade 4, but we may be exposed to the idea. So the one with the terms being related to the set of counting numbers or natural numbers is not to be discussed at the grade 4 level. Not with the degree of sophistry that we have in this problem, or likely to have in a similar problem, but we can be exposed to the idea at this level. Watch this now. 18, 21, 24, blank 30. Terms in a sequence are related to the natural numbers. We may begin at 1, but that will be too harsh. What number may we begin at?
18.
What counting number? What number? Let me see if Jerry can identify. There's a number that is related to 18, and then the very next number after that number is related to 21.
3.
And the next number after that is related to 24. What number you may put right here is related to 18. Then the very next number after that one is related to 21. then the very next number after that one is related to 24. What number do you know is related to 18? Then the very next number after that number is related to 21. Then the very next number after that one is related to 24. How is 6 related to 18?
Because 6 into 18 goes 3 times, and 7 into 21 goes 3 times.
6 into 18 goes 3 times.
Right.
So what number do we put here?
7.
7 into 21 goes?
3 times.
What number do we put here?
8 into 24 goes 3 times.
Right.
And 9 into 27 goes 3 times, and 10 into 30 goes 3 times.
Correct. So that is what we have right there. So what number may we begin at? We can begin at 1. We should really begin at 1, but it is going to be too sophisticated at this level. What are the numbers to which 18, 21, and 24 are related? In the same way, how are they related to them? 6, 7, and 8. Multiply each by 3. So we have 6 3s 18, 7 3s 21, 8 3s 24. Since the relation is true, the other term is related to 9 because we are going up. We have 6, 7, 8. What is the next number?
9.
9. And we will do what with 9?
9 times 3.
9 3s 27. And that is our correct answer. So since the relation is true, the other term is related to 9. To be conclusive, 30 must be related to the next number, the next natural number. So it must be related to what number comes after the 9?
10.
Right. What number comes after the 9?
10.
Okay. So 6, 7, 8, 9, and then 10. Right. So we showed on the previous slide that consecutive terms in a sequence are related to each other. Here we are seeing that consecutive terms or terms in a sequence are also related to the set of natural numbers, and they can be shown to be related to the set of natural numbers. So we have 6, 7, 8, 9, 10. In a sequence, consecutive terms are related to each other, and the terms are related to the natural numbers. What is 86 rounded to the nearest 10? 86 rounded to the nearest 10.
90.
Speak up.
90.
Right. So we have 86 rounded to the nearest 10. When rounding a number to a particular place value, the digit of focus is the one at that place value. So we are focusing on that place value. We are rounding to the nearest 10. So we are at the tens place value. That is the digit of focus. We then consider the very next digit, which is the one of less significance. So we will consider that one. We consider that digit. If that digit is equal to 5 or more, then we add 1 to the digit of focus. Is it greater than or equal to 5?
Yes, it is.
Yes, it is. Therefore, we will add 1 to the 8, and the result will be?
9.
Right. So 8 plus 1 is equal to 9. 86 cannot be approximated to 9. in order that the 9 will retain the place value of the 8, a place holding 0 has to be included right there. And Jerry stated that the result would have been 90, and it is. The correct answer is therefore option
B.
If the digit of less significance were 5, we would still add 1 to the digit in the place value in question. If it were less than 5, then the digit would have retained its value. So if the next digit were a 5, then we would still add 1 to the 8. But if it is less than 5, then we would not add 1 to the 8. What is 83? We are putting in another problem of our own. What is 83 rounded to the nearest 10?
80.
And Jerry is saying that that is 80. Let us see. When rounding a number to a particular place value, the digit of focus is the one at that place value. So we are rounding to the nearest 10. So the digit is the 10th digit that we need to focus on. We then consider the very next digit of less significance. We then consider the digit of less significance. If that digit is equal to 5 or more, then we add 1 to the digit of focus. Is it?
No.
It is not. Do we add 1 to the 8?
No.
So the 8 will be returned as it is. 83 cannot be approximated to 8. In order that the 8 will retain the same place value as before, a place holding 0 has to be included. Rounding a number is actually making an approximation. Rounding 86 is not approximately 9, and rounding 83 is not approximately 8. In order that the digit in question might retain its place value, place holding zeros may be included. They may also be necessary to be included. Which pair of fractions is equivalent? Which pair of fractions, Jerry, will give the same?
A.
Jerry is saying that it is A. Jerry is correct on this occasion also. They represent equivalent fractions. What are equivalent fractions? They are fractions that have the same value, but their terms are in different forms. Or we may say that they are in different terms. They have the same value, but they are in different terms. What makes this problem simple is that all of the second fractions have a numerator of 1. So we will show, well, Jerry figured that out already, but we are going to demonstrate by calculations and manipulations how we may arrive at our conclusion. And in this particular case, the first principles that we are about to apply, those principles are made simple to be explained because the second fraction, each of the numerator is equal to 1. 1 multiplied by any number is the same number. The numerator of the other fractions will be the factors by which terms are multiplied. So we are saying that we are going to investigate all of these fractions or pairs of fractions for equivalence. So we are going to try to see if we can get these fractions to turn out to be the same in the end. But what number do we multiply by? If these fractions are equivalent, when we multiply the fraction, both numerator and denominator, by a particular number, then we will get this one. Let us say this one for argument's sake. If we are trying to show that these two are equivalent, we have a 1 here. And what do we have here, Jerry?
4.
In multiplying, how do we get from 1 to 4? What number do we multiply 1 by in order to get 4?
1. 4.
Right, we multiply 1 by 4. What number do we multiply 1 by in order to get 3?
1 by 3.
Right, we'll get multiply by 3. What number do we multiply 1 by in order to get 2?
2.
Right, so it is easy to determine what number we should multiply by because all of these numerators are equal to 1. So 1 multiplied by any number is that same number. The numerators of the other fractions will be the factors by which terms are multiplied. And we'll do it all at once. So for this one, we will multiply by 4. And for the other one, we'll multiply by 4 also. So these two will have the same factors that we multiply by. And this one we multiply by 3. So let's go. When we multiply both numerator and the denominator by the same factor, or we say by a common factor, then these are the result. When we multiply like this, we get 4 ones,
4.
4 twos,
8.
then we have 4 ones,
4.
4 twos,
8.
3 ones,
3.
3 twos,
6.
right, and then so on and so forth. In the end, which two fractions are equal? The ones in option
A.
right. So we are sure that option A represents equivalent fractions. There we have the fractions that are the same, those two. For example, in this particular case, if we are looking at or focusing on the numerator, it does not make any sense that we multiply by any other number than the number that would give us the 3. And it is easy to determine which number will give us the 3, because the number that we have here is 1. So the transfer is easy. There we have the fractions that are the same, and they are representing option A. The correct answer is therefore option
A.
On the next slide, we will take a look at ways that we might determine that fractions are equivalent. So on the next slide, we will take a look at ways that we might determine that fractions are equivalent. Fractions are equivalent if when we multiply both numerator and denominator of one of them by a common factor, the answer is equal to the other one. So we have 4 over 8. If we multiply both numerator and denominator by, say, 4, 4 ones, 4, 4 twos, 8. Since we multiply both numerator and denominator of the fraction by the same number, and we have the result being equal to the first fraction, then we know that a half is equivalent to 4 over 8, because the result is actually 4 over 8. When we multiply both numerator and denominator of a half by 4, the answer is the same, 4 over 8. A half and 4 over 8 are equivalent. If by reducing, dividing both numerator and denominator of one by a common factor, we get the other, the two fractions are equivalent. Right, so let us take a look at that. If we divide both numerator and denominator by a common factor and we get 2 over 3, then 10 over 15 and 2 over 3 are actually equivalent. So what number do we use? 5. 10 divided by 5 is equal to 2. And 15 divided by 5 is equal to 3. We get 2 over 3 as we have right here. When we divide both numerator and denominator of 10 over 15 by 5, the resulting fraction is 2 over 3. 10 over 15 and 2 over 3 are therefore equivalent fractions. We have another way of doing it. If we have two fractions and we multiply the numerator and denominator of the first by a common factor, then do the same to the other fraction. If the same fraction results, then the original fractions are equivalent. So let's do that. So we multiply 4 over 6 by 5 over 5. 5 4s?
20.
5 6s?
30.
Then we say 2 10s?
20.
2 15s?
30.
Right. So we multiplied the two fractions that we had there, one by 5 over 5 and the other by 2 over 2, and the results are the same. Both numerator and denominator of 4 over 6 were multiplied by 5. Then both numerator and denominator of 10 over 15 were multiplied by 2. Both operations yielded 20 over 30 as the result. 4 over 6 and 10 over 15 are therefore equivalent fractions. If a particular fraction of a whole may be represented by two fractions, then those two fractions are equivalent. Did you hear that, Jerry? If a particular fraction or part of a whole may be represented by two fractions, then those two fractions are equivalent. We will take a look at that also. We will show that a portion of a whole may be represented by different fractions, and that is what we mean by equivalent fractions. We'll show that physically. And we are at our original problem again. Which pair of fractions is equivalent? When attempting to prove whether fractions are equivalent, we need a factor to multiply or reduce by, as we did, remember, on the previous slide?
Yes.
This one we multiplied by 4. This one we multiplied by 4 also. What did we use to multiply this one?
3.
And what did we use to multiply this one? 2, right? So we need something to multiply. We may choose a factor based on the numerator or denominator. On the previous slide, we chose one based on the numerator. The one in the numerator makes it easy in this particular case. 1 is transferable to any number by multiplying by that same number. So if we have a fraction, say, Jerry, if we have a fraction like 3 over 4, and we have another fraction that we want to know if that fraction is equivalent to 3 over 4. The numerator of that fraction is 18. What is the factor that we need to multiply by?
6.
Yes, we need to multiply by 6. Or 6 is one number that we could use, because 3 to be transferred to 18, we need to multiply that by 6. So 6 is a factor that we could use. In this particular case, all the numerators are equal to 1. Therefore, it is easy to use the numerator to arrive at a number that we should use to multiply. So 1 is transferable to any number by multiplying by that same number. Transfer 1 to 4 by saying 1 multiplied by 4 is equal to 4. And transfer 1 to 3 by saying 1 multiplied by 3 is equal to
3.
And so on. We did that before. Transfer 2 also. 1 multiplied by 2 is equal to 2. So we have done that for all of those. We could have compared the denominators also in attempting to prove that the fractions are equivalent. Because we can compare the numerator, we can also compare the denominator. Right. So what we did just now is make use of the fact that to transfer 1 to something else by a multiplication by a particular factor is very easy. Because if we have 10 and the other one is 1, what do we multiply by?
10.
And if we have a numerator of 1 and the other one has a numerator of 7, what do we multiply by?
7.
That's easy. We could have compared the denominators also in attempting to prove that the fractions are equivalent. We will take a look at how we might do so on the next slide. On this occasion, we will choose our factor from the denominator. Right, our factor will come from the denominator on this occasion. So there we have our denominators, and our denominators are equal to 2. Well, Jerry, if you cannot answer this question, you cannot survive. If we need to transfer 2 to 8, what factor do we multiply by?
8.
If we are transferring 2, not 1, 2, if we are transferring 2 to 8, what number do we multiply by?
4.
And if we are transferring 2 to 12, what number do we multiply by?
4.
If we are transferring 2 to 12, what number do we multiply by? We are multiplying by a particular number. If we multiply by a particular number and we have 2, what number do we multiply by in order to give 12?
6.
And in order to get 10, right, we multiply 2. Right, so we can see that for those denominators that we have there, the transfer is actually also very simple. So in option A, we need to transfer 2 to 8. We therefore need to determine the number that will multiply by 2 to give 8. 2 times 4 is equal to 8. Use 4 to multiply both numerator and denominator. In B, what number will multiply 2 to give 12? Jerry said that it is 6. 2 times 6 will give 12. Our factor is 6. In C, the denominator is also 12. So we'll do the same thing. For D, our factor is 5. So 2 times 5 will give us 10. So we could have compared not only the numerator and choose our number to multiply by based on the relationship between the numerator of the two fractions, but we can choose our factor based on the denominator of the two fractions. So when we do that, what do we get? Right. So when we multiply, what do we get? In the first case, we multiply by 4, as indicated. 2 times 4 is equal to 8. So we multiply both numerator and denominator by 4. The result is 4 over 8. Because we are focusing on the denominator, 2 6s 12. So our factor, we call that 6. 6 over 6 to multiply. And the same thing for option C. And to move from 2 to 10, we multiply by 5. So the factor that we use right there is 5. Still, only option A is shown to be correct. So only in option A did we get the same fractions resulting when we did our multiplication. And as a matter of fact, we know that option A is correct. Therefore, if we change our approach, if we change the method, if we change the numbers that we use, we will still arrive at the fact that option A is correct as long as our method is legitimate. When the factor is found, it may be used to reduce the other fraction. Multiplication is easier than division. The number is not always divisible, but we may always multiply. So when a factor is found, it may be used to reduce. That means we divide both numerator and denominator by that factor. Or we may multiply. The number is not always divisible, but they may always be multiplied. Take a circle and divide it into equal parts. Take a circle and divide it into equal parts 3 times. That's what we are doing. And what we are doing here, we are attempting to show that equivalent fractions may result from dividing a whole into a number of equal parts. So we have the same size circle, and in the first case it is divided into how many equal parts, Jerry?
8.
8 equal parts. Each part is called an eighth. And what is the denominator associated with that one, Jerry? The denominator associated with dividing an object into 8 equal parts.
8.
The first has 8 equal parts. Its denominator is?
8.
What about the second one?
4.
4 equal parts. Its denominator is?
4.
The other one, how many equal parts?
2.
Its denominator is?
2.
The second circle is divided into 2 equal parts, which is the third circle is divided into 2 equal parts. Its fraction will have a denominator that is equal to 2. Shade equal parts of the 3 circles. Well, we are going to shade. What fraction is that, Jerry?
Half.
Right, we are shading half of each of the circles. Half, we are shading half. But we shade half of this one. This circle, we have shaded half of this one, and this one. But let me ask you, in terms of this that we have here, the denominator of 8, what is the fraction that we should have there?
4/8.
Right, we have 4/8. Right, so shade equal parts of the circle. That represents 4/8. How many parts of each whole is shaded? So the first one, Jerry is saying that it represents how many eighths?
4/8.
And the second one represents
2/4.
2/4, right, or 2/4. And the last one represents
A half.
a half. Are all of those fractions equal?
Yes.
All of those fractions are equal. So equal portions are represented by 4/8, 2/4, and 1/2. They are all halves, right? It therefore means that the fractions are all equivalent. That means those fractions, as Jerry said, that they are all halves. They are all equivalent to a half. So 4/8, 2/4, and 1/2, they are all halves. all of them are equivalent to a half, irrespective of the form that they are in. When counting by tens, which number would come after 30? What number comes exactly after 30 if we are counting by? What number comes immediately after 30 if we are counting by 10? And Jerry is saying that is represented by option
C.
Option C. But let's see. When counting by tens, the digit in the tens position will increase by 1 each time. So when we are counting by 10, the digit in the tens position will increase by 1 each time. When it reaches 10, the hundreds digit will increase by 1 and the tens digit will start again from 0 like so. This is because the digit to the left is always 10 times the current place value. In this particular case, the hundreds digit is 10 times 10, or 10 times the tens digit. There is the number in the statement of the problem. Increase the tens digit by 1. So that's what we are doing. If we are counting by tens, it is the tens digit that goes up by 1 each time. So we have 30. What will come after 30 if we are counting by 10? We need to increase the tens digit by 1. And this is how we do it, Jerry. 1 click and it goes over to 40. And that is our correct answer. The correct answer is option C, as Jerry stated before. Let's go again. With the understanding that when counting by tens, the digit in the tens position will increase by 1 each time, we may just add 1 to the tens digit. Right. We need to add 1 to it. And we will physically add it on this occasion. This is how we add it. So we may just add 1 to the tens digit in 30. 3 plus 1 is equal to?
4.
And then, do we finish there?
No.
What will happen?
Carry down the 0.
With nothing to be added to the other digit, it will return as it is. Very bad mathematics. The correct answer is therefore option C. That is really a crude way to add 1 to the tens digit and may only be suitable for rough work. On the next slide, we will take a look at the appropriate way to do it. So on the next slide, we will take a look at the appropriate way to do it. This may only be used for rough work. As a matter of fact, in my practice, I do not encourage rough work. I always encourage students to do everything like you are presenting it to an examiner. And by so doing, students' work, the work that is presented to me is generally above average presentation. So this is the correct way to do it. The one that will be added to the tens should be shown to be 110. And if so be the case, its place value should be included. So it should be shown to be the tens digit. And for it to be the tens digit, the accompanying place holding 0 is necessary. So 0 plus 0 is equal to?
0.
3 plus 1 is equal to?
4.
The correct answer is option
C.
Option C. When counting in tens, when we get to 10, 1 is added to the hundreds digit and the tens digit returns to 0. On the next slide, we will take a look at why this is so. Let us count in tens as usual. This is done by continually adding 1 to the tens digit. Continually adding 1 to the tens digit. Continually adding 1 to the tens digit. Let us continue to count. We need to add 1 to the tens digit. On this occasion, we will do regular addition rather than just flip the digit. So we will not flip the digit on this occasion, but we will add. So we will add 1 to the tens digit. And if we are doing that, we need to show that it is actually the tens digit by also including the ones digit, which is a 0. 0 plus 0, Jerry, that's your favorite addition. And then this one, 1 plus 9 is equal to?
10.
So write down the 0 and carry 1 to the hundreds column, just like normal addition. And then we finish up by 1 plus 2 is equal to?
3.
This is why when we are at 9 tens, we get to 100 by increasing the tens digit by 1 and returning the tens digit to 0. It is the same as saying that 10 tens make 100. So when we are counting in tens, we increase by 1 each time. When we get to a number like 290 and we add 1 to the tens digit, 1 plus 9 equals 10. We put 0 and carry 1. And that is why when we are counting and we get to 9 tens, if we add or we count another 10, it will go, the tens digit will go to 0 and 1 will be added to the hundreds digit. And that is the same as saying 10 tens make 100. Let us continue with number 8. Which of the numbers, when divided by both 2 and 3, does not have a remainder? Which? It does not have a remainder. When you divide that number by 2, it does not have a remainder. When you divide it by 3, it does not have a remainder. 12 is the correct answer. This problem may be solved in many different ways. In this first attempt, we will make use of the knowledge of the numbers that each of 2 and 3 may divide into without a remainder. Therefore, we will make use of what we call the multiples of 2 and 3. Those numbers are called multiples of 2 and 3. And are the same numbers that form their multiplication tables. So the numbers that we will make use of, the multiples of 3, are those numbers in your 3 times multiplication table. Not all of them. And multiples of 2 are those in the 2 times table also. The number that may be divided by both 2 and 3 without a remainder is that number among the options that is present in both lists. So, we have multiples of 3. Those are the numbers that 3 may divide into without leaving a remainder. And we have the multiples of 2. Those are the numbers that 2 may divide into without leaving a remainder. So in order to determine the number that may be divided by both 2 and 3 without leaving a remainder, we need to identify the numbers that are in both lists. What are the numbers that are in both lists, Jerry?
12.
And? We have another number that is in both lists. What other number apart from 12 is in both lists?
6.
Right. Right. But what Jerry is focusing on is the number that is in both lists that is present in the option. And that is 12. And that is our correct answer. So the number that may be divided by both 2 and 3 without a remainder is that number among the options that is present in both lists. Notice that 12 is present in both lists, and it is the one in the option. The only number in the options that is present in both lists is 12, and it is representing option C. As we mentioned before, 6 is also present in both lists, which means that 6 may be divided by both 2 and 3 without leaving a remainder. But if we consider the numbers that are inside of those options, we realize that 6 is not among the options. 12 is among the options. Therefore, the correct answer is 12. Two and 3 do not have any common prime factor. It means that the correct answer must also be a multiple of 2 times 3, which is equal to 6. Any number that is a multiple of 2 and 3 is also a multiple of 6. I hope you noticed that, Jerry, that those numbers that are both multiples of 2 and 3, they are also multiples of 6. Therefore, we may choose our answer from multiples of 6. So take a look at some multiples of 6. They are the items in our 6 times multiplication table. Multiples of 6. 6, 12, 18, 24, 30, 36. Right. Those numbers are multiples of 6. Those numbers are also multiples of 2 and 3. It means that 2 and 3 may divide into those numbers, every single one of them, without leaving a remainder. The number that may be divided by both 2 and 3 without a remainder is that number among the options that is present in the list of multiples of 6. So, in the list of multiples of 6, only 12 is present among the options. Therefore, our correct answer is
option C.
Right. All multiples of 6 are multiples of both 2 and 3, but 12 is the one that is in the options. Option C is therefore correct. Another approach that could have been used is to divide each number in the options by 2 and 3 and find the one that leaves no remainder. So we could have gone through the entire option, dividing each one by 2 and 3. Solutions that are based on the manipulation of the options are very poor methods and reduces the necessity to learn and make use of fundamental principles. Such practices reduce the student's ability to transition to the next level. Also, if the answer is present in the last option, the process may be unnecessarily lengthy in an examination. When students are sharp on fundamental principles, they may even glance and identify the correct answer. So, we can manipulate each one of those options by dividing each one by 2 and 3 and see the one that leaves no remainder in both cases. But, as stated right here, solutions that are based on manipulation of the options are very poor methods and reduces the necessity to learn and make use of fundamental principles. Such practices reduce the student's ability to transition to the next level. Also, if the answer is present in the last option, the process may be unnecessarily lengthy in an examination. When students are sharp on fundamental principles, they may even glance and identify the correct answer. Before moving on to the other problem, let us establish a mathematical fact. So we are about to solve a problem, but we are establishing a fact before we move merrily along. What do you notice about those numbers, Jerry?
The numerators are all 12.
Right. The numerators are all 12. They are all the same. Take a look at those fractions. What do we notice? We notice that the numerators are all the same.
They can be divided within each other without leaving a remainder.
Well, the form that we have there, you said that you also noticed that we may divide without leaving a remainder. I designed it that way especially so that when it divides, it does not leave a remainder. But there is something else that you need to pay attention to. They all have the same numerator. We said that before. In a fraction, the numerator is divided by the denominator. So let us show those divisions. What will the first answer be, Jerry?
1.
And the second one?
2.
The third one?
3. 4. 6. 12.
Right, so those are the answers. Do you notice anything about the denominators? Do you notice?
Counting down.
And yes, Jerry is saying that they are counting down. But I would prefer to say that they are going down or decreasing in value each time. The denominators are decreasing in values each time. And what do we notice about anything else? We notice that the denominators are decreasing each time. They are getting smaller each time. What about the answers? What do you notice about the answers?
They are going up.
Right, the value is going up. Therefore, the answer is getting larger each time. They are getting larger each time. It is a fact that if the numerator does not change and we decrease the size of the denominator, then the answer will increase. So we have a constant value in the numerator and we are decreasing the value of the denominator. The result is increasing. As we divide by a smaller number, the answer gets larger. What fraction is the largest in value, therefore? Which one would be the largest in value? The fact that we establish is that when you decrease the number that you are dividing by, the answer increases. When you decrease the number that you are dividing by, the answer increases. Which fraction is the least in value? Let me see what we are saying about that right now. Just like on the previous demonstration slide, all of the fractions have the same numerator. We have also established that as the denominator decreases, the answer increases. The converse is also true. As the denominator increases, the answer
decreases.
Right. So which one will have the least value then?
3. 2. No.
Option
B.
B. Right. Option B will have the smallest or be the least in value. Why will it be the least in value? Because we are dividing by the largest number. So when we are dividing by the largest number, the result will be the smallest, as long as the number that we are dividing into remains constant. And we have it right there that the numerators are all the same. Therefore, the largest denominator will give us the smallest answer. When we increase the denominator, the answer will get smaller. Which one will therefore be the smallest fraction?
1/5.
1/5. The one with the largest denominator will represent the smallest value. Option B is therefore correct. Conversely, the one with the smallest denominator has the largest value. The largest fraction is a half. Remember, this is only true if all of the numerators are equal. If all of the numerators are equal, then the one with the smallest denominator will be the largest value. And the one with the largest denominator will be the smallest value. Let's see if we can establish that right there. Take a circle and divide it into equal parts 3 times. The denominator will be what in this particular case?
8.
The first has 8 equal parts. The denominator is 8. In the second case, the denominator will be?
4.
The second has 4 equal parts. The denominator is?
4.
And the other denominator will be?
2.
Each numerator is 1. This tells us that the number of equal parts that we are talking about is equal to?
1.
So each numerator is 1. So the number of equal parts of the whole we are talking about is 1. So if it is 8 equal parts, it's 1/8. And it is 4 equal parts, it is?
1/4.
1/4. And if it is 2 equal parts, it is? Half. Shade one part of each circle. Which one is the smallest? Of the shaded portion, which one is the smallest?
1/8.
Right, because you can obviously see that 1/8 is the smallest, right?
Yes.
Right, it is the smallest. What else do we notice? That it is the largest denominator.
Yes.
Okay. Which one is the largest shaded portion?
Half.
Half is the largest shaded portion. What is the denominator?
2.
Right, so the largest shaded portion has the smallest denominator. And the smallest shaded portion has the?
Largest denominator.
Right. The 8 is the one with the largest denominator, and it is the smallest one, while the half is the one with the smallest denominator, and it is the largest one. Which fraction is the same as 5/6? And we did another problem before, and Jerry is answering already that it is option
D.
Option D is the same as 5/6. Therefore, we will take steps to demonstrate how we arrive at D, which is 25/30. And we did a problem just now extensively demonstrating how to manipulate equivalent fractions. And now we are required to do the same. Which fraction is the same as 5/6? What helps to simplify this problem is that the options all have the same
Denominator.
right, they all have the same denominator. Therefore, we are sure that the problem is easy to solve. And we'll show that the problem is made simpler by all of the denominators being the same. Since one has to be correct, it means that the denominator of 5/6 must be transferable to 30. Let me see if Jerry can transfer it. 5/6. So the 6 must be transferred to
30.
what number do you multiply 6 by? And the result is 30.
5.
Right. So the common factor that you will multiply both numerator and denominator by is 5. 5/6. That is the fraction that we want to know which one is the same as 5/6. We need to transfer 6 to 30 because all of the denominators are 30. Therefore, the denominator of the correct answer must also be 30. All of them are 30. So we cannot escape from 30. The correct answer must also have a denominator of 30. We need to transfer 6 to 30. What number do we use to multiply 6 in order that the result is 30? That is the same as saying 30 divided by 6. We should know it straight away. Our multiplication table will tell us. And we did not even need to include it there, because Jerry, even before the problem was properly asked, Jerry figured out that the correct answer is option D. The number that we will multiply by is 5 because we need to transfer 6 to 30. 6 5s, 30. So 30 is our target. 6 is where we are starting at, and 5 is what we use to get there. So we will multiply by 5. But we cannot do it to the denominator alone. That will change the value of the fraction. We need to do it to the numerator also. So multiply by 5/5. What do we get? 5 5s.
25.
5 6s.
30.
There we have it. 25/30. The correct answer is therefore option
D.
right. What fraction is the same as 5/6? We are doing some more investigation. So we are dabbling a bit with mathematical principles. One alternative that is not so quick is to reduce each of the fractions to their lowest terms. Option A may be reduced by a common factor of 5. 5 into 5?
1.
5 into 30?
6.
So the result will therefore be 1/6. 5 into 5?
1.
5 into 30?
6.
The correct answer is therefore 1/6. Option B may be reduced by a common factor of
6.
6. How do we know that we may reduce option B by a common factor of 6, Jerry?
Because 6 into 6 goes 1 time and 6 into 30 goes 5 times.
Because 6 can actually go into the numerator and the denominator. It is a common factor of both numerator and denominator. Right. And Jerry worked it out already that 6 into 6 is 1 and 6 into 30 is 5. So we say 6 divided by 6, that's equal to 1. And then 6 into 30, we will get 5. So the result is 1/5. What about option C? The numerator and denominator of option C, what can we reduce that by?
Nothing.
There is no common factor except 1. There is no common prime factor of the numerator and denominator of option C. So it may not be reduced. So option C may not be reduced. We already know that option D is correct. All that we need to do is reduce it by a common factor of 5 to prove our point. So we will take 25 over 30 and we will reduce that by a common factor of 5 into 25,
5 times
5 into 30.
6.
Right. The answer is
5, 6.
Therefore, we have shown that 25 over 30 is actually the same as 5/6. Multiplying the numerator and denominator of a fraction by the same number does not change its value, only its form. And we say that the terms are different. So we will say that when the fractions are equivalent, they are equal, but they are in different terms. We will continue with number 11. Which two numbers give a total of 110? Which two numbers give a total of 110? And that problem may be solved in many different ways. But I will demonstrate to you, Jerry, that if you understand or you are quite familiar with the digits and which ones are the pairs that add to give 10, then your problem may be greatly simplified. If you are sharp on your digits, one look and you would figure out the answer right away.
Option D.
And Jerry is saying that it is option D because he wants to prove all the time that he is sharp on his digit. But for this one, pay attention, Jerry, because you will see this problem solved in a way that you never imagined. What do you notice that I am highlighting, Jerry?
The 5s.
Why am I highlighting the 5s? Because when you add these, what do you get?
10, 20, 10, 10, 10.
Right, because when you add those pairs of 5, the result is 10. So all you need to do is add the rest of the digits to get 100. And that is also simple if you know the digits that add to give 10. So each number ends with a 5. So this causes the end digits, which are the ones digit, to have a sum of 10. The other digits must have a sum of 100. So the 5s are highlighted. In each case, those 5s will add to give 10. Therefore, we only need to get the sum that will give 100. It will also benefit us if we can spot at sight other pairs of digits that have a sum of 10. So you, Jerry, tell me some digits that you know, 2 digits that add to give 10.
4 and 6.
4 and 6. What else?
2 and 8.
What else?
5 and 5.
Another? You did not say 3 plus 7.
3 plus 7.
And you did not say, let's see if you can figure out the one that you did not say.
9 plus 1.
That is the one that you left out, Jerry. So all of those will have a sum of 10. The other digits that we have are the tens digits. If they have a sum of 10, that will be 10 tens, which will be 100. And that is what we need. Do you understand that, Jerry?
Yes.
Okay. So let us repeat that. The digits that we have here, that we have added to get 10, out of the 110, it means that the other digits should add to give 100. But because these digits that we have here are the tens digits, when you add them and you get 10, 10 tens make 100. So there you will get your 100. Among the sums that give 10, the digits that match are in option
D.
Option D. So we are sure that option D is our correct answer. So add the 2 5s, we get 10. We need to add the tens digit to get 10. So 10 tens, 100. So we just need to look at the pairs and see which pair will add to give 10. And we have 4 plus 6, and that's equal to
10.
as we have in the list of pairs of digits that add to give 10. So these being tens digit, 10 tens, 100, and we have solved the problem already. So the correct answer is option D. The sum is judiciously divided into 2 parts. 5 plus 5 equals
10.
and the rest that will give a sum of 100. 40 plus 60 is equal to 100. And we will do a little bit of investigation on the next slide in order to bring home our point more clearly. There we have, what number is this, Jerry?
110.
Right. There we have 110. As we said before, the sum will be easy to analyze if we separate it into 100 plus 10. By applying a bit of common sense, the answer may be easily figured out mentally. So we have the 100 and we have the 10. So separate it into 100 and 10. 2 components, 100 and 10. So what do we have over here? There we have the optional pairs. Remove the 5s, they give a sum of 10. Right. So the pairs that we have here are the pairs in the option. So we will remove the 5s because each pair of 5 will give a sum of
10.
Right. So remove those. That is what we will have. Our focus is now on the tens digits. Which pair has tens digits that have a sum of 10? Which pair gives a sum of 10? The tens digit give a sum of 10.
40 and 60.
40 and 60. Right. 40 and 60. The tens digit with a sum of 10 are 4 and 6. They belong to option D. 10 tens are equal to
100.
100. So these are the tens digits. If we add them and we get 10, that will make 100, which is what we want. And that will be our correct answer, which is option D. So which number gives a total of 110? Again, we will resolve 110 into two components, which are 100 and 10. So there we have 100 and we have 10. Use the 5s to give the sum of 10. The 5s will give a sum of 10. Let us add 40 and 60.
100.
Right, Jerry is saying that's 100. So that will give 0, and 6 plus 4 will give us 10. So we will put 0 down, and we will carry 1 to the greater or the more significant position. And in the end, only the one that was carried is now in the hundreds column. So it will go there and we get 100. So we will see that if we have to begin with 45 and 60, we may just add those 5s to get 10, and then the 40 with the 60 will give 100, and that's all there is to it. The simplicity in the question was caused by the numbers which add quite easily to give 10. Let us show it again using different numbers. So we will show the same thing using different numbers, that the same principle may be applied as long as the digits will add to give 10. So there we have our 110 as before, with all the digits, with all the place values, and we have there 78 and 32, right? So again, we will resolve 110 into two components, which are 100 and 10. There we go. Use 8 and 2 and see what happens. The 8 and the 2 will easily give a sum of 10. So let us add 70 and 30.
100.
100, as we did before. Add the tens digit. 7 plus 3 is equal to 10. Only the one that was carried is now in the hundreds column, so we will cause it to take its rightful place. When solving a problem, examine it to see if there is anything that makes it simple. We make use of pairs of digits that have a sum of 10, right? So if we can see quite easily something that makes the problem simple, then we may use it. And in this particular case, we saw that the digits will have a sum of 10, and that makes it simple for us. We are about to solve another problem. But what do we know? The other problem that we are about to solve is quite cumbersome. Therefore, on the next few slides, we will do or make use of some information that we will use as background information in solving the problem. So let us make use of that information. First of all, we have a little portion of our 8 times table. We will be dividing by 8. So let us throw in a few items from our 8 times table that we have at the top there. Before solving the next problem, let us do some calculations, and we will use these calculations as background information in solving the problem. There we have 200, and we intend to divide 200 by 8. Help me now, Jerry. we are dividing 200 by 8. 8 into 2.
I can't.
8 into 20.
2 times.
Okay. So attempt to divide 8 into 2. We can't. So we say 8 into 20 equals 2. Attempt to divide 8 into 2. We can't. So we say 8 into 20 equals 2 and place the 2 above the 0. Then what do we say? 8 times 2 equals 16. Subtract the result from 20. So 2 8s, 16. Subtract that. What do we get when we subtract, Jerry?
4.
4. What do we do after we get 4?
Bring down the 0.
Right, so the 0 will accompany the 4 as the next number to be divided by 8. 8 into 40, Jerry?
5 times.
5 times. So we will then say 8 into 40 goes 5 times, and then we say 5 8s?
40.
So we say 5 8s 40 and minus that 40 from the 40 that we have there. And what will be the result? 40 minus 40 is equal to 0. So we have exhausted all of the digits in the dividend, and also the result that we have there crumbled to 0. There is no digit remaining in the dividend, and the last subtracted result is 0. The problem is therefore at an end. So when we divide 8 into 200, what do we get, Jerry?
25.
That you have to bear in mind when we are solving the problem. So here's another one that we need to do. Multiply. We will be multiplying by 8. So let us throw in a few items from our 8 times table, and we have done that already at the top. When multiplying numbers, we begin with the numbers that are at the right. They are the ones with the smallest place values. So we will begin right there. 8 4s.
32.
It is a good thing that I have Jerry working with, because sometimes I lapse in concentration and I might say the wrong thing. 8 4s, 32. What do we do?
Put down the 2 and carry the 2.
Right.
10th column.
Great. Write down 2 and carry 3 to the next column. The place value to the immediate left is always 10 times the present place value. That is why for each result, the tens digit is carried to the left. So if we have a number like this standing alone, this is 32, which means 3 tens and 2 ones. The ones will remain in its rightful place, and the 3 tens will be carried to the left column, in which we find the place value of greater significance, whose value is 10 times the present place value. So 2 and carry 3. Then we say 8 2s.
16.
And then we say 16 plus the 3 that was carried, and we get 19. Write down 9 and carry 1 to the next column. But because there is nothing there to multiply, the 1 will be carried into the product just as it is. The 1 that was carried to the hundreds column is the only digit there. It was not a part of the initial problem and should not be multiplied. If we had something else to multiply, it would have been a part of the sum. So 1 plus whatever it was, that's what we would normally do. But in this particular case, there is no sum. So 1 plus 0 is equal to 1. And 24 multiplied by 8 is therefore 192. Right. And do not forget that, Jerry. 24 times 8 will give us 192. when we are solving the problem, we might not be able to do the other calculations at the same time. Therefore, we are doing the calculations before, that when we get to them, we will just make reference to them because we would have done them already. There are 24 sodas in each case. But what case? Andy's mother needs 200 sodas for a party. There are 24 sodas in each case. How many cases of soda will she need? How many cases of soda will she need? There are 24 sodas in each case. The number of cases must be less than the number of sodas. To find the number of cases, we divide 200 by 24. 24 is quite a number to divide by, so let us do it this way. So we have 200 sodas and 24 in each case. We need to know how many cases according to the statement of the problem that we have there. How many cases of soda will she need? Let's see what Jerry makes of this one. I know that Jerry will make a meal of this one. 200 divided by 24. Jerry is saying that he will not make a meal of it. Well, let's see.
8.
I'm not saying a word. Not yet. So we say 24 is quite a number to divide by. So let us do it this way. So instead of dividing 200 by 24, we realize that 200 and 24, they have what? Common factors. So tell me a number that you know that can go into 24 and it can go into 200. Jerry?
6. 4.
4. Right. We intend to divide 200 by 24 because the numbers are quite large, especially that there is a common factor that we may divide by. We will write in a fractional form. And then we will reduce the fraction by a common factor of 8. So Jerry said that we have a common factor of 4. That is correct. But we are reducing it to the best of our ability. And in order to do that, we are attempting to use the largest number that can divide into 224. So remember the calculations on the previous slide. Remember that, Jerry?
Yes.
When we divided 200 by 8 and the result was what? Can you remember? When we divided 200?
25.
Right. It was?
25.
25. Right. Good. So 25. So we are reducing by a common factor of 8. But we did not do the calculation for 24 because that is not far-fetched. So we reduce 24. Reduce that first. 200 divided by 8. And we said that was, what did we get?
25.
We got 25. And then we say 24 divided by 8. And that will give us what?
3.
24 divided by 8
3.
will give us 3. So there we have it. 3. So the fraction now is reduced to 25 over 3, meaning that we should divide 25 by 3. Very nice.
3.8.33.
All right. So 200 divided by 24 is the same as 200 over 24. The fraction was reduced by a common factor of 8 to 25 over 3, which is the same as 25 divided by 3. And we will do that on the next slide. So we reduce that by a common factor of 8. We got 25 over 3, which is the same as 25 divided by 3. So we will divide 25 by 3 on this slide. Instead of the large 200 divided by 24, let us go ahead and use the reduced form, 25 divided by 3. So let's do that. 3 into 2.
I can't.
3 into 25.
8 times.
Okay. So attempt to divide 3 into 2. We can't. So we say 3 into 25 equals
8 times.
and place the 8 above the 5. Watch this now, Jerry. 3 8s.
24.
Subtract the result from 25. That is what Jerry is saying that we should do. And he has been saying that for quite some time, that we will get a remainder of 1. Well, there it is, Jerry. There is your remainder of 1. So 3 8 24. Subtract that from 25. And what do we get?
21.
We get 1. So that's your remainder. The quotient, which is the answer, is 8. As Jerry said, 8. And he's contending that it is option B. But I do not say that it is option B. I say that the quotient is 8. And there is a remainder of 1. But Jerry is very surprised that I am not choosing 8 as my answer. We may say that a fraction of a case remains, or extra bottles of soda remain. So we know that they are extras, right?
Yes.
If she purchases only 8 cases, the additional ones will be left out, and she will not get to 200 sodas. She needs to buy 9 cases. If she does not buy another case, she will never get to her 200 cases. If the remainder is just 1 soda, she still needs to purchase another case. The correct answer is option C, because of the leftovers, Jerry. If she's purchasing 200 sodas, she needs 200 sodas. Needs 200 sodas. 24 in each case. We divide 200 by 24. When we do that, we get 8, and they are remainders. It means that if we use 8, we will not get the 200 because they are leftovers. So we have to purchase a number of cases that will give her the 200. So we will have to purchase more than the 8 cases, else she will not get the 200. And we will see that before we are through. There are 24 sodas in a case, and the answer is 8 cases. Remember that on our previous slide, we multiplied 24 by
8.
When we multiplied 24 by 8, what did we get?
192.
How many sodas does she need?
200.
Right. So if we use 8 cases, we'll just get 192 sodas. We will not get 200 sodas. Right, it will be short by 8. The answer is 192 when we multiply. If she buys 8 cases of 24 sodas, she will get only 192 sodas. But she needs 200. The only way that she can reach her goal of 200 sodas is if she includes another case. The other case will cause the total number of sodas to exceed 200. But this is better than having less. This is how it is with some problem in mathematics. If we round off to the nearest whole number, we will not achieve our goal. We have to include another unit. So 8 plus 1 is equal to 9. When we divide by 3, the remainder was 1. This is not 1 soda because the problem was reduced 200 minus 192 is equal to 8. Also, the problem was reduced by a factor of 8. Therefore, the remainder of 1 means that 1 multiplied by 8 is equal to 8. So, we are short by 8. We are not short by 1. We divide by 3. The remainder is 1. But do not forget that the problem was reduced by a common factor of 8. So when we get the remainder, we need to increase also the remainder by a common factor of 8. So 8 ones will be equal to 8. And 8 is what we will have for the unreduced problem.